Welcome to the Collaborative Science for Story series. This is Nick Sobral with the Science Collaborative. Today's webinar features a collaborative research project that evaluated uncrewed aerial systems as a tool for measuring reef changes within 5 National Estuarine Research Reserves from North Carolina to Florida. You'll hear more detail from some members of the project team who have joined us today, but before we get started, I've got a few quick housekeeping points, as I mentioned, including some introduction to the Science Collaborative, the reserve system, and this webinar series. The National Estuarine Research Reserve System is a national network of 30 unique research reserves as shown on this map. It's a NOAA program that works in collaboration with a local place-based partner, either a state agency, university, or nonprofit at each site. Each reserve site includes programs focused on the activities you see on the slide, showed there on the left. The Science Collaborative supports science for estuarine and coastal decision makers by coordinating regular funding opportunities and supporting user-driven collaborative research and transfer activities that address critical coastal management needs identified by the reserves. The Collaborative Science for Story series features project teams supported by the Science Collaborative, program staff, and partners. Speakers share their unique approaches to addressing current coastal and estuarine management issues. If that sounds interesting to you, please feel free to join us for future webinars to learn about new methods to integrate experts and users into their research process and how their research results and products might inform your work. A quick note on informed consent. Webinars are a valuable learning opportunity for us as a program. Insights from speakers and participants like you can help inform how we support others in doing collaborative science. For example, in the development of future workshops, webinars, or resources such as tools, tips, and case studies that we add to our guide to collaborative science, which is open source, open access, I should say. With that in mind, we want to inform attendees that insights or feedback that you share with us, for example, in chat or via the webinar exit survey, may be used for program learning and development. Please note that if we capture a direct quote from you that we like to use for learning purposes, we will reach out to you beforehand to seek permission and provide an explanation of its use. All such quotes will be used anonymously, and we're grateful for the opportunity to learn alongside you. So lastly, some housekeeping stuff. All attendees are muted upon entry. We'll be handling the presentation-related questions via Zoom's Q&A feature that you can find in your little console there that kind of floats and disappears. You can enter questions for presenters as they occur to you throughout the webinar, and we'll plan to discuss as many as we can at the end. The chat is visible to all, or it will be once I open it up after I finish talking here. You can use that to talk amongst yourselves or let organizers know if you have any technical questions. We can answer them that way. And with that, I'll introduce our speakers for today. Peter Kingsley Smith is the Assistant Director of the Marine Resources Research Institute within the South Carolina Department of Natural Resources. Brandon Puckett is a research biologist in the Coastal Resilience Restoration and Assessment Branch of NOAA's National Centers for Coastal Ocean Science. And Justin Ridge is the research coordinator at the North Carolina National Estuarine Research Reserve. And I will stop screen share so that Brandon can take over, and I will open up chat so everyone can talk to each other.
All right, great. Well, appreciate the opportunity to speak with you this afternoon. I'm going to talk to you about a regional project here we have going on. So our project that we're going to talk about is focused on oyster reefs that present something of a unique management challenge because they are both a foundational species, but also susceptible to both recreational and commercial harvesting. And so managers and restoration practitioners have expressed a need for novel methods of assessing the condition of these oyster reef habitats. And so the goal of this project is to conduct a regionally coordinated effort spanning from North Carolina to Florida to determine the ability of imagery derived from drones to estimate common metrics associated with intertidal oyster reef condition. And with drones, there's a lot to like. Centimeter scale resolution, a lot of high level of control over the temporal frequency of sampling, and so on. And so today we want to share with you a regional project that's worked with and within 5 National Estuarine Research Reserves in the southeastern United States, as those highlighted on the left here, from the North Carolina NERRs, the North Winyah Bay NERR, the Ace Basin NERR, the Sapelo Island NERR in Georgia, and then the GTM. I was going to try and have a crack at the acronym there for a minute, but then I thought more wisely of it, and I'll just go with the GTM reserve. So the logos and the key members of the project team are highlighted here as well. The project was supported by NOAA staff as well as a graduate student at NC State University, and funding for this project was provided by the NERRs Science Collaborative and NOAA's National Centers for Coastal Ocean Science. So within the southeastern United States, oyster reefs provide some critical ecosystem services that are probably familiar to many of you. They improve both water quality and clarity through their filter feeding activities. They provide habitat, such as to this oyster toadfish here, aptly named, being a highly reef-associated critter. In many recent years, our group has also done a lot of work looking at the shoreline protection feature of some of these fringing reefs, acting as natural breakwaters to protect the adjacent salt marsh from the erosive forces of currents, winds, waves, and storms. And then largely, as I mentioned in the earlier introduction, oyster reefs support both recreational and commercial fisheries. And what's challenging here is that in many cases, the destructive manual harvesting practices associated with these recreational and commercial fisheries sort of fly in the face of the ecosystem services that these reefs are treasured for. Furthermore, as this illustration from the Nature Conservancy's publication in 2011 by Beck et al. Shows that they are in peril on a global scale. And shellfish reefs at risk became sort of akin to the coral reefs at risk document that put the imperiled nature of tropical coral reefs on the same footing as these sort of more temperate analogs, if you will. So Natural Resource Agency users on the project team have expressed a need for affordable, non-destructive approaches to rapidly and quantitatively monitoring and assessing oyster reefs at useful spatial and temporal scales. Such information could then be used to inform the allocation of scarce resources, such as the allocation of shell and loose shell planting, for fisheries enhancement or restoration, as well as to support sustainable management of recreational and commercial harvest activities. But these methods need to reflect the needs of managers to assess the structure and condition of oyster reefs and to detect changes over time. So this need for novel approaches was really where this project came in. And so we reached out to our end users and tried to get a sense as to what sort of the key metrics are associated with reef that are illustrative of like healthy, productive reef condition. And these indicators also need to be relevant through changes in space and time. So conceptually, on this picture of an intertidal oyster reef, I want to highlight some priority indicators and identified by managers on our project team. So first, this is reef height and elevation, and this is important for a couple of different regards. A high reef elevation indicates that the reef is highly productive with lots of vertically growing clusters of oysters. But vertical elevation also has benefits in terms of protection of the salt marsh and also resiliency against things like sea level rise and climate change. Another metric is aerial extent. In many cases, oyster reefs are managed based on their acreage. And there may be fees associated with the exact acreage of a particular reef in a particular management area. And so assessing accurately the extent of the reef and being able to differentiate reef from non-reef habitat is a key metric here. We saw that picture of the oyster toadfish, and there's well-established studies that link structural complexity to reef-associated diversity. And so getting a sense as to what structural complexity is in terms of things like rugosity, being the sort of the absolute distance across the contour over the sort of straight line run, if you will, was also a metric that rose to the top of being something that the managers were very interested in. Percent cover, equally a measure of sort of reef health. Greater amounts of sort of interstitial mudflat and non-reef habitat may indicate that the reef is more sparse than something that has higher percentage cover. And in many cases, we're able to identify that living veneer as being that percent cover of live oysters on the surface of the reef. Shell volume is useful in many ways. One example of where they might be useful would be to look at the efficacy of shell planting. So if we have a particular volume of bushels of shells that we know that we're using for restoration, and we plant those on a particular reef, then we can perhaps use drones to measure shell volume and look at what our effectiveness or efficiency is, how much of that shell volume is actually being integrated into the reef over time. Abundance. Everybody wants to know how many oysters are on the reef, particularly if it's how many market-size oysters are on the reef. Okay, and so moving ahead to the structure of the project a little bit more, the project has 4 main objectives, which I'm just going to read to you, so I apologize for that. I'm pretty sure you guys can read. Objective 1, use drone-derived spectral and 3-dimensional products to estimate priority structural and demographic metrics. Many of those that we've just talked about: reef elevation, footprint, rugosity, etc. Objective 2, to conduct in situ measurements of reef metrics identified in Objective 1 to assess the accuracy of uncrewed aerial systems-based estimates. Objective 3, to assess the ability of UAS-derived products to detect and quantify changes in reef metric. Objective 4 was to compare in situ and UAS methods in terms of comparing efforts, costs, and benefits. So with that, I'll hand over to our second speaker this afternoon, Brandon Puckett.
Thanks for that introduction, Peter. And so with those objectives in mind, I think it's important to note that we're really building on previous research that has used remote sensing as a tool, certainly not the only tool, but as a tool to assess oyster reefs. And so, for instance, Grizzle et al. 2018 essentially developed a relationship between satellite-derived image color with estimates of in situ based estimates of oyster density, so shown here on the y-axis, such that oyster density increased from image class 1, so these are sort of the white off-white pixels, pretty low density, to image class 3, which are the sort of brown olive green shades of satellite imagery. In the early to mid 2000s, the state of South Carolina used imagery collected from airplanes essentially to conduct more or less a statewide delineation of reef footprints, which I've shown kind of outlined in the red here, and with a relatively high degree of accuracy. Hoffman et al. 2023 off the coast of Germany used a time series of digital surface models, essentially derived from drone products, to look at changes in elevation, seasonal changes in elevation over time. So the panel on the left here, where you see the orange colors, is increase in elevation from March to September of 2020. And the panel on the right is in blue are decreases in elevation from September to the following March. I think an important note from the Hoffman et al. Work is this notion of limit of detection, which essentially says, based on the error associated with your elevation models, you can, with some statistical significant or confidence, determine what sort of elevation changes are real versus sort of what is noise and beneath your detection limit. And then lastly, highlight some work from Wendell et al. 2022, who at a couple reefs in North Carolina essentially pulled spectral and structural information out of drone-derived imagery to predict via statistical models oyster density, and as shown here in the plot with in situ density on the x-axis and predicted density on the y-axis, they did so with a pretty tight relationship. And so what I think our project does is not only build on this work and incorporate much of it, is that we sort of expand the number of metrics that we're quantifying. So Peter went over the 6 metrics that our end users identified as key priority metrics for them. We're doing so over a pretty large geographic area, so the South Atlantic Bight, and also developing kind of detailed recipe-like, if you will, workflows for each of these metrics that'll be open access and publicly available on our project website. So, okay. So how did we go about doing this work? So I'll cover sort of the in situ ground-based sampling methods first, and then switch over to the drone stuff. So for elevation and extent, we used real-time kinematic GPS surveys and did that across sort of axial profiles on the reef, and then also went around and traced reef boundaries. For Rugosity, we used what is sort of the chain and tape method, whereby we kind of painstakingly, I would say, fed this little ball and chain into all the little nooks and crannies of this reef and tried to stay as linear as possible. And then, as Peter mentioned, you measure the straight line distance versus the distance of the profile of the reef. And we usually, depending on the reef, had 3 to 6 replicate Rugosity chains per reef. Percent cover was done using square meter quadrats. We tried to estimate percent cover of live oyster, shell or culch material, and then mud. I should note here that different reserves did this a bit differently. Some used a point intercept based approach, some used kind of just a visual ocular method, and others just took a picture of the quadrat, brought it back to the computer, and used ImageJ to estimate percent cover. And we did 3 to 12 replicates per reef per percent cover. And then lastly, for density and volume, we excavated quarter meter by quarter meter quadrats, so 1/16 of a square meter excavated, brought all those samples back to the lab and counted and measured oysters, and then estimated the volume of material we excavated via water displacement. And we did 3 to 6 replicates per reef for that. For the drone-based sampling and image processing, we used sort of consumer-grade quadcopters with pretty standard red, green, blue sensors. We did target flying at low tide, and I will say a big strength of drones is the user's ability to temporally define when they fly. So low tide is important when the reefs are exposed. We also targeted solar noon based on some literature we had read. It does mitigate shadowing on the reef, although it comes at the expense of having a bit of glare on the water and potentially on some exposed mud. We set front and side overlap of our image collection at 75% and flew at an altitude such that each pixel was about 1 centimeter by 1 centimeter square on the ground. We did deploy 12 ground control points, generally speaking, in and around the reefs, and surveyed those in with RTK GPS, and then put out some checkpoints to assess the horizontal accuracy of our models. I will say that the ground control points are really important for improving kind of the georectification of the products you get from your drone-derived imagery. We flew before and after we excavated the quadrats, and that was the after flights were largely to look at volumetric change following our excavations. And then used structure for motion software to generate the two, namely the two products that are shown below. So a digital surface model whereby sort of each pixel has an XY coordinate as well as an elevation coordinate, but no real color. And you can see this is just a small swath of a reef, but it almost looks like the popcorn ceiling. So you do get some texture there, and you can see the structure. And then at the bottom of that is an orthomosaic, which is essentially the composite, the seamless composite of all the images collected. And so there, each pixel has an XY coordinate and a color. And then we tried to purposefully keep all of the analyses in ArcGIS Pro and essentially Excel, programs that our end users and us, importantly, are very comfortable using. And then I should say that we did all of this across about 40 reefs at the 5 reserves, and we tried to do this across different sort of reef morphologies, so fringing and patch reefs, as well as different management regimes. So harvested reefs here, where you can sort of see there isn't much structure, versus protected reefs, where you can see there is quite a bit of structure. And I think pretty cool at GTM, at least, there was areas that were sheltered from boat wake, and then those that were exposed to boat wake. Okay, so I guess now I want to go through the results of, I'll go through each of the 6 the results for each of the 6 metrics that we worked on. And I want to give a big shout out to those that really got us here. So in no particular order, Camille Steenrod, Dan Bowling, Gary Sundin, Laura Sanchez, and Alex North. I think that pretty much covers everyone. If I forgot anybody, I apologize, but huge kudos to them for really doing much of the work that I'm going to present on here. And so we'll start with reef elevation. So here on the left is kind of a digital elevation model of one of our sites. And then the sort of a cutout of the ortho here. Basically, we can assess the accuracy of our elevation models using our RTK shots all over the reef, which are what those little dots on the orthomosaic are. Right? And so if we use that extract values to point tool in ARC, we can do just that. And I'm showing sort of for this reef the relationship between what we measure in situ on the x-axis using our RTK with what we estimate from our surface model. And so just to orient you, because I'm going to show a lot of these, recall that our objective 3 is say, hey, how do your drone-derived estimates compare with your in situ estimates? So just to orient you, pretty simple kind of correlation-ish plot. So I'll have in situ on the x-axis, generally drone-derived stuff on the y-axis, and the symbols are observations. The solid line is the best fitting linear regression, and then the dashed line is the one-to-one line, which is sort of perfect agreement, right? And so what we see here for this reef is that, well, the relationship is really tight, pretty good R-squared, and it falls right along that one-to-one line, which is good. And this is generally the pattern we see for all the reefs. Our surface models are generally pretty accurate. And we assess the accuracy using a root mean squared error, and reported here on the figure in centimeters. Across 4 reserves we have a lot of elevation data from. So North Carolina in the north, south to GTM in Florida. And so root mean squared errors in these blue bars here. And you can see it varies a bit among our sites, ranging from 1.5 centimeters at North Inlet Winyah Bay to about 4 centimeters at Ace Basin. And over the course of all these sites and all these reefs, it's on average about 2.7 centimeters, which is really, really pretty good in my opinion. I mentioned the Hoffman et al. Work and their inclusion of limit of detections based on the root mean square error of successive surface models. And that's an important thing when you think about things like volumetric change. So I did want to share some of that here. So it is important to get your root mean squared errors of your surface models as low as possible, or else you really can't detect much change, right? So the red bars on this graph are limit of detection, and that ranges from about 2 centimeters to about 6 centimeters, but on average is around 3.8 centimeters. And just for reference, this is the height of a legal sized oyster. And just sort of a take home here is that surface models really are the backbone for everything that comes. So it's really imperative to get them as accurate as possible. And with the current technology, at least, I think a best practice is still necessitates getting out on the ground and putting out ground control points, and really also shooting RTK shots all along your reef for which you can estimate sort of an actualized root mean square error. Okay, next is Rugosity. And Peter mentioned this. It's sort of our measure of structural complexity. It's the ratio of kind of the straight line of the profile distance, so the distance to go up and down all the nooks and crannies versus the straight line distance. And a rugosity of 1 is sort of a flat surface, and ratios greater than 1 indicate increasing levels of reef complexity. And so what I've tried to do here, it's really based on the surface model. This is just a slice of a surface model, and here's sort of a theoretical rugosity chain. And this is sort of the profile that you see along the reef. And we do pick up quite a bit of complexity, in my opinion. It's a really neat exercise to just look at profiles along the reefs, I think. And so we can use a tool in ArcGIS, the Add Surface Info tool, which gives us essentially the distance it takes to traverse all of this, and we would know our straight line distance, so we can calculate rugosity as that ratio. And so here, as I mentioned, I'm going to share quite a few of these kind of in situ versus drone-based estimates for these metrics. So again, in situ rugosity on the x-axis, rugosity estimated from our surface model on the y-axis. And we have the different colored symbols are data from different reserves. And sort of what we know here is first is that, well, there's a general positive relationship between in situ and drone-derived estimates, albeit kind of loose. R-squared is not super high. And perhaps more importantly, we generally are underestimating rugosity from drone-derived products. Basically, all of those observations you see fall beneath that one-to-one line. And this underestimation seems to be really a function of ground sampling distance. So at a few reefs in North Carolina, we did sort of a sensitivity analysis of sorts, whereby we altered our altitude, which changes your ground sampling distance. So the orange line is a ground sampling distance of 1 centimeter per pixel. And as we improve and get more resolute, fly lower and get a finer ground sampling distance of 0.5 centimeter per pixel, you notice the blue line kind of approaches that one-to-one a little more closely. And so it's kind of the take home from that is that with drones, there's always this trade-off, right, between resolution So your ground sampling distance and what you can cover over space, right? At least with current battery limitations and whatnot. So I think it's important to know that the scale that you're interested in for your particular application before you sort of design your flight parameters. We also did, in addition to sort of just putting chains on reefs, we did sort of a manipulative experiment, and I'll highlight some work here, and used Rugosity as one of the responses. So the picture on the left, you can see Lauren and Lexi out there with their culling hammers, and they're out there culling oysters and throwing the legal sized oysters in buckets. And so we can measure rugosity or its change before and after that harvest. The picture on the right, the little green box, is a control area where nobody went, no harvest was done, nothing was added, etc. And then Gary is working in the addition plot where he's taken everything that was harvested out of the harvest area and putting it on bare mud flat, right? And so we can look at the response of that, which I've shown here. So we have 3 stanzas. So the rugosity before harvest, rugosity post-harvest, and then rugosity post-addition. And so this is rugosity on the y-axis here. So the blue bars are a function of this harvest experiment, right? So what you would expect after harvest, or at least what I expected after harvest, was rugosity to go down, right? You remove things, it gets less complex, and we do see that, right? It does happen. There's also instances where rugosity stays pretty constant over time, and then yet where rugosity counterintuitively, I think, sort of decreases or increases, excuse me, after harvest. And in some of our in situ data did reflect the same trend. And some of our, you can make really big divots harvesting and increase your rugosity. So it's maybe not the best metric or the only metric you should use to look at the impacts of harvest, right? So in our green plot out here, the control plot where nothing changed, we see that across the experiment, rugosity on a mudflat and on a reef stayed pretty much more or less constant. And then out here where Gary is adding shell on a mudflat, we generally, not shell, but clusters of oysters, we generally increase in rugosity following that addition. The last point I want to make about rugosity is traditionally we have measured it in this linear fashion with this chain and tape approach, and it makes very little sense to do that actually with imagery. It really makes a lot more sense to look at a ratio of 3D surface area versus 2D area. And so what Gary did here with the hand delineated reefs is do just that. He estimated the 3D area of the reef versus the 2D area, and where you can see reefs in green have a relatively high rugosity and those in red relatively low rugosity. We can also do that at a different scale. We can overlay a grid on a reef and estimate rugosity at sort of square meter scales if we'd like. And so here red is higher rugosity and the pale yellow is lower rugosity. Okay, third is reef footprint. This workflow is a little bit more complicated than the others, so I'm going to go into a little more detail and try to walk you through that here. The input is an orthomosaic, so an RGB orthomosaic is what you sort of start with. And if you desire, you can sort of clip that and zoom in a bit to the reef you're focused on. Followed by kind of stretching the raster, which really functions to enhance the contrast in the image. And then you can segment the raster, and what that does is group the pixels into objects, which creates a more object-based approach for classification. And I think it can help really reduce some of the salt and pepper effect you get when you're working with like 1 centimeter scale pixels like you do with drone imagery oftentimes. The user provides training samples, and I want to make a note here that there is some subjectivity here. Pretty much all of the other workflows, like any user can go through it and generate very, very similar results. There is some art and some science to these training samples, and in our workflows, we provide some best management practices for generating them. But just want to note there that there is a bit of subjectivity and user specificity there. So with the training samples, you run it through the classifier. We used random tree or support vector machine. You can also add additional rasters. They generally, like a surface model, that it does generally improve your classification success. And out of all that, you get a trained classifier, your classified raster, and you can assess accuracy and whatnot. And so just on the right here is sort of the original reef here, and then the classified version here, where the sort of magenta and pink colors are oyster shell, and everything else is either water or sediment. And so here's just a blow up of kind of the reef classification with the accuracy assessment points overlaid. And so each of these points, you're assessing whether the classification was correct. And that generates a confusion matrix from which we can estimate a kappa value, which gets at sort of your overall classification accuracy, with a kappa of 1 being perfect and a kappa of 0 being completely random. And so here are some data from 4 reserves, so Ace Basin, GTM, North Inlet, and North Carolina. And so what you see across all those reefs is that our kappa values range from about 0.55 to 0.92. But on average across all the reefs are 0.8, which is in kappa parlance significant, for whatever that means. But overall, really good, actually, classification success across a range of different reef types and geographies and whatnot. I do want to say that I think a take home here also is that the more complex your reefscape or landscape, and or the greater number of classes you try to classify across, generally speaking, the lower your classification success is going to be. But the products we can generate from the footprint workflow are many. So that you can get the delineated ecotone, which is sort of a tracing of the outer boundary of the reef. This is what we tried to do with our RTK as well. And I'll just say that the RTK surveys and this delineation generally agree pretty well. You can get reef extent, which gives you sort of a reef area. The classified footprint, sort of in the middle here, gives you perimeter area ratio or percent cover of shell versus not shell, those types of things. And I think for application, we'd all be interested in doing sort of change over time in footprint. And so we've shown that here, where the blue is sort of gain in shell, red is loss, and tan is stable. All right, number 4 is percent cover of live oysters, and I'm going to focus on sort of the live oyster category for this portion. I mentioned the footprint. We can get sort of the estimate of percent cover of shell versus not shell. So for live oyster, we use the ortho and DSM. So ortho mosaic and DSM, again, to go through that supervised classification. So again, building on that footprint workflow to get our classification map. And that gets us to shell versus not shell. And then we used an additional raster, which is a derivative of the surface model, called the terrain roughness index, which is essentially a pixel elevation relative to a neighborhood. And we use that to estimate percent cover of what we're calling 3-dimensional, like the vertical part of the reef. And we assume that is live oyster. And so in this picture here with the quadrat, like the little red area, would be a TRI where it's vertical, and we can estimate the area of that within that quadrat. All right, so here's the in situ versus drone based estimate. So in situ again on the x-axis, TRI based estimate on the y-axis. And what I've done here is averaged across replicates on a given reef for both approaches. And I did that because, as I mentioned earlier on, for the in situ work, reserves used 3 different approaches to measure percent cover, and that was to say point intercept, ocular, or image J. And the variance around those is plus or minus 15 or 20% if you look at the same quadrat. So I have averaged around here, and the take home here is that, again, there's pretty good agreement between what we estimate in situ versus what we estimate based on this terrain roughness index. Across really, I think, a pretty wide gradient of percent cover. So 10% to somewhere around 75% live cover. The one thing, again, that I'll highlight, and I sort of highlighted this for the rugosity stuff is that, for in situ sampling on a swath like this, we may have one replicate, yet we can grid across the reef and have hundreds of replicates, right? So what that does is really increases your sampling size and power. And so just to demonstrate that here, I have borrowed some work from Elia Bennett's master's thesis that she worked on behalf of the project. And what I've shown here on the left is mean live oyster percent cover on the y-axis across a few different sort of reef regimes on the x-axis. So we have exposed to boat wake versus sheltered, some control reef, and harvested versus non-harvested. And we have 12 replicates, right? And so you might expect that the reef exposed to boat wake would have less live cover than that sheltered, which this sort of bears out. But we don't have statistical power to detect any difference between all these. And in fact, harvested has more percent cover estimate than non-harvested, which is sort of atypical what we might expect. But if we take the drone based products, and again, we've done this, you grid it over the entire reef, so you have an N well greater than 1,000. We can look at mean live oyster cover again across those different reef types. And so at least a priori wise, we see the differences and are able to detect the differences that we might expect. So exposed has lower percent cover than sheltered, and harvested has lower percent cover than unharvested. And we can statistically, with some degree of statistical confidence, detect those differences. And so again, I think a take home there is this sort of the increased sample size of these kind of virtual quadrats via this grid really increases your statistical power. All right, fifth, volumetric change. The workflow here really builds off of Hoffman et al.'s 2023 work, and it's simply sort of raster subtraction. So you take your basically raster subtraction of surface models from the same reef in a time series. But here for us, it's kind of the post-excavation surface model minus the pre-excavation surface model. So the way our project's designed, that is, those flights are an hour apart or a couple hours apart. So you really wouldn't expect to see much difference on this subtraction raster here, which you don't. All the purple colors basically are 0. I think you can kind of see some footprints of us walking along the reef. But generally speaking, there's not a whole lot of difference in elevation between pre and post, except where we went out and did our excavations. So you can see that pretty good. And I'm just blowing it up here, where the blue and cyan colors are a loss in elevation where we excavated material. And then we can essentially apply our limit of detection threshold, which is again based on the root mean square errors of both of these surface models, to only calculate volumetric change across the pixels which exceed the limits of detection, either more negative or more positive, and then multiply that essentially by the size of our pixel. So we know the area of every pixel, we know the elevation change of each pixel that exceeds that LOD, and we can sum those to get our volumetric change. And so we did that. So here's the sort of the in situ on the x-axis up here versus our volumetric change based on our surface models on the y-axis there. And the dots are just observations across different reserves, and the solid line is the best fitting linear regression, which, as it shows from the equation here, is it's pretty scattered data, right? There's not, I mean, there's a general agreement, but not a very strong relationship. And so I think partially that has to do with the scale at which we're removing stuff. This is on the scale of sort of a bushel across the entire reef or something, that we're pretty small scale removal. I mentioned earlier, we did do these sort of manipulative experiments where we tried to work at a little bit larger scale. So these are kind of 25 square meter plots here. After we went and harvested them, then we threw some shell on there as sort of a restoration mimicking strategy. And you can see where we added the shell, all this white stuff here, you sort of pick that up in elevation gain. So that's done at larger scale. So in the order of kind of 5 bushels of removal and 5 bushels of addition. And so if I show that plot here again, in situ volumetric change here, surface model volumetric change there. These are the data right here from the previous slide. So they're almost centered on 0, 0 on the plane here. So very, very small removals from our quadrat excavation. And this, 5 bushels, we start to see Maybe a little tighter relationship, but we're still processing a lot of this data, so we'll see if that relationship holds. Still a pretty crude and loose relationship. So and then lastly, I just want to share, in North Carolina, we had took advantage of an opportunity to go out pre and post a large sort of mitigation project where they were moving oysters from a dredged area to a protected area. And so moving on the order of 15 to 120 bushels. And so these data right here are from this graph up here. And then so much larger scale additions there. The relationship increases, but again, you know, linear regression, super sensitive to these extreme observations. So much more could be done there, but I think the take home is that more to be done with volumetric change, and it's pretty scale dependent. And then lastly, density. So the approach here, again, building largely on Anna Wendell's work, was to use sort of orthomosaics, isocluster, which is essentially an unsupervised classification of the orthomosaic such that pixels are either light, intermediate, or dark. And then surface models, and then the TRI as well. For each of the quadrats, we calculated the zonal statistics for all of those rasters, which generated like some 36 explanatory variables, of which we could use in statistical modeling approach to try to predict density. So we used a generalized additive modeling approach, and we did that in R. This is sort of the only thing we couldn't do exclusively in ARC and Excel. First of all, we looked at univariate relationships for all 36 explanatory variables, and then did sort of a stepwise approach to develop our multivariate model. And I've shown sort of the GAMs for the four factors that was significant for total oyster density, and those were the percent of dark pixels. Again, recall Ray's work suggesting that the brown and dark olive colors tended to be associated with increased density. Max elevation relative to mean low water, sum of our terrain roughness index, and then latitude. Notably here, GTM is they didn't measure total density, so we don't see that typical South Atlantic parallel sort of relationship that we thought, but latitude was significant regardless. And on the y-axis is the partial additive effect of each factor on density. So for instance, this relationship is pretty linear, but as the percentage of dark pixels increase, so too does density. And we did that for total density, recruit densities, which are less than 25 millimeters, submarket oysters, which are 25 to 75 millimeter, and then anything greater than 75 millimeter was market density. And so the in situ versus predicted estimates are shown here across 4 reserves. And so the take home here is that the relationship for total densities actually is pretty strong, similar to what Anna Wendell got. Although I should note that the models that she generated did not work well for our data, even if it's the same 2 reefs that she flew. So we use the same framework, but different factors. And interestingly, the relationship for recruit, submarket, and market oysters, our predictions there tended to decrease, which is a bit counterintuitive, right? We're not really seeing recruits on the reefs, although we're pretty good at predicting their abundance relative to our in situ sampling. Whereas I would think the drones could see the larger market-sized oysters, but we really aren't very good at predicting them, and adjusted R-square of 0.51. I haven't completely wrapped my head around as to why that is, so more to be done there. But again, we can generate some really, I think, pretty neat maps at least at reef scales that we've not been able to do before. So here is a map of recruit density, or predicted recruit density, whereby the darker, the redder, more dark orange colors are higher predicted recruit density. Over a small little patch reef shown here. And I mean, some of it makes sense right away. Like for instance, this area here is just a big sand flat that kind of comes in the reef. Some of this area here is really high elevation, so it's probably too high for good recruitment, etc. And importantly, I think, is uncertainty with those estimates, so we can generate the standard error maps for the same recruit densities. And so I think one of the take homes for me here is that these types of maps really open up our ability to kind of investigate some spatially explicit, at least at the reef scale, ecological or harvest or restoration patterns that really haven't been possible before. Okay, this is my last slide before passing on to Justin. I did want to touch base a little bit on Objective 4, which is kind of this cost effort analysis. And again, borrowing some data from data that Elia collected as part of her thesis. And so what I've shown here is sort of the cost for a kind of a 5-year monitoring program, broken down sort of per year, per reef, and per meter squared. And it's a pretty exhaustive, I think, accounting effort to try to figure this out. And it includes things like equipment. So if you need a drone or a boat or a truck or something like that, that's included. So it's really if you're starting a program, essentially. Supplies, so everything from drone batteries to marsh boots to pencils and all that kind of stuff. Software, so your ArcGIS licenses, your structure from motion software, labor rates, training. So thinking about training it required for getting your Part 107 license, or training in how to sample in situ or process imagery. And then lastly is sort of the time required, hours required to measure things in the lab and analyze imagery and that kind of stuff. And so what you notice is that I think the two approaches, generally speaking, are pretty close on kind of a per year basis. So I don't know, 45, 50K per year is the estimate for this is for North Carolina and GTM data only, I should say. The per reef estimate is about 3K for an in situ effort and 6.5 for drone. Largely that difference is driven by the fact that GTM, as part of their annual sort of in situ monitoring, monitored across 39 reefs and only flew 5. So quite a discrepancy there. And then I think perhaps importantly is like when you look at it on what you get spatially per unit area, the drone-based approach is really an order of magnitude cheaper. It just, you need to make sure that increased area coverage is important for the questions that you were trying to ask, I think. And just to give folks an idea of sort of what it takes for kind of the drone-based kind of everything from data collection to imagery analysis, we estimate that kind of out in the field is 3 to 4 hours per flight area. That's boat ride, getting out there, and that's 2 or 3 people. Image processing is sort of 1 to 2 hours of active time, 3 to 4 hours of total time. And then image analysis for all those 6 metrics is, we kind of depends on the person and the reef and everything, but 11 to 15 hours for those 6 metrics. So broken down accordingly. And like I said, footprint's really the most involved. It takes quite a while, but all the other workflows, generally speaking, are a couple hours a reef or something like that. So not a trivial exercise, but thought that might be useful for people thinking about this approach for their work. All right, Justin and I will turn it over to you now.
All right, thanks, Brandon. I'm just going to do a quick recap of what Brandon and Peter just were talking about and some next steps. So to begin with, just talking about our objectives. So what we noticed with the drone versus the ground comparison data, we had our drone estimates actually correlated with our ground-based estimates, and but that varied between the metrics. So we had a little bit of, we had correlations, but the strengths of those varied. What we did notice though, is that variability in metrics collection of those on the reefs, when you have your sampling on the ground, you actually get a lot more variability in the, in your ground sampling, but doesn't necessarily equate to what the actual reef looks like. And so you get a lot less variability and a lot more of a holistic view of the reef using the drones. And that increased sample size that you're able to extract across the reef, gives you a little bit more statistical power to actually detect differences. Then we noticed, as Brandon mentioned, when you're trying to detect change, that was our objective 3, that you that was scale dependent in some of our metrics. So some of those metrics were really good, regardless of kind of what scale, but sometimes you couldn't really look at quadrant scale. You had to look at the reef scale. But overall, we were able to see reef scale changes that were observable from our drone metrics. And then limitations on drones. So this is like the drone weighed down by these things that can't just like fly freely. Drones, we've seen that they're a cost-effective, powerful tool, and they can be operated at these user-defined temporal scales. But, what we're advocating is we still notice there's still this whole challenge of reef access and the deployment of ground control points, because where technology is not quite there yet, where we can just operate without ground control if we really need really good elevation data. And certain metrics still require ground data for model training. And also the spatial coverage, the spatial coverage that we can consider, you can't really drone the entire coast. It's still sort of limited in that aspect. So the optimal monitoring and assessment approach at scale was likely a combination of approaches. And that's from your ground to your drone to your satellite. Next steps. So the first thing, and Brandon mentioned this, we are going to be sharing those workflows. And so they're going to be posted online and through the NERRs Science Collaborative website, so that everyone can access those workflows and play with them, use them. From that, we're going to engage. We're going to continue engagement with our Oyster resource managers and other interested partners to gain feedback on those workflows, and hoping to have further dialogue with this interstate collaboration and help shape the next phase of our project that we're hoping to pursue. And with that, we're going to be exploring all the data that we so the first step of that is exploring all the data we've collected. This project focused on testing the methods and seeing what works, but we have all this data that we've collected across the Southeast that we want to take a deeper dive into and really kind of explore high resolution, spatially explicit ecological patterns and processes across the reefs that we've been studying. And that'll lead us into, since we can create all these data layers from the drone data, and we'll be exploring those relationships across the Southeast, our goal is to integrate these layers into a multi-metric reef conditioned index that could be applied more holistically to track changes in reefs. And then we want to apply that and work with our project reserves and our partner oyster resource management agencies to apply that index across the region and collaborate on the process for incorporating these tools into management practices. And I just want to acknowledge the team that has contributed to this, integral people that have collected and processed, analyzed all these different aspects of the data and helped us create what we've shown you today. So that's it, right?
That's it.
Q&A.
Q&A. All right, we've got a few minutes left, folks, so don't be shy. If you have questions, feel free to pop them into the Q&A or the chat, and we will verbalize them before we head out. Let me put us in gallery view here so you can see all the speakers. All right. No questions yet. That's how good your presentation was. You explained everything so perfectly that no one has any questions.
Amazing.
I'm just kidding. One question coming in. All right.
I mean, that was true for me. I don't know about Brandon and Justin.
Okay.
Max X in the chat. How high are you flying to get a 0.5 centimeter resolution? Yeah, that depends on the airframe and the sensor really, Max. I think for a lot of this work, we were using Phantom 4s, which are now probably pretty obsolete, but still workhorses. We would be flying at about I don't know, maybe 15, 20 meters, something like that, which is pretty low. Now, Eric, he has an Enterprise, Matrice 210 or something, and he could probably get away with flying at 30 or 40 meters and still get the same resolution. So it really depends on the sensor and airframe being used.
Okay, another question here. Did you come across any challenges in creating training samples for the classification maps? Is there an optimal number of training samples you should create?
Yeah, I should let Dan, I don't know if Dan could be unmuted. He really is the footprint guru. Yes, there are obstacles to creating your training samples. And what we've found is that you have to do a really good job of covering your bases, and some of your training samples really need to be kind of small in terms of not overlapping multiple classes that you would want to generate in your classifier. It's a tricky thing. In terms of the number, I can't remember what we put in the workflow, but there is we've done some looking at how many training samples provide and accuracy, and we came up with some estimate for best practice as to what you should try to aim for at kind of a reef scale. If I don't know, Nick, if you can unmute Dan to let him chime in on some of that. He knows more about, he's forgotten more about that workflow today than I'll ever probably know. So
yeah, Dan, I'll let you talk, so you can go ahead and unmute.
Sure, thank you, Brandon. I hope y'all can hear me. Yeah,
Yep.
It does vary from site to site. At a minimum, you'll want to have at least 20 training samples per strata. And then you could have as many as 150 with a sort of average coverage of about 100 per strata. And the key there is to really kind of highlight the spectral color variation that is presented at an equal representation across the site.
yeah, thanks, Dan.
Thank you. Couple more questions in the chat here. Maybe we'll end with this last one. Have you tested any linear corrections for the ground versus drone-based measurements, or what are your thoughts on the consistency of the offset of the relationships?
Yeah, that's a good question. Stephen, we have not done that really, except for elevation. We did use our in situ data and the very small offset, honestly, usually a y-intercept correction, but sometimes a slope correction as well, to reduce the root mean square error of our elevation models, simply because it's so critical to everything that follows and your limits of detection and that kind of stuff. For things like rugosity and whatnot, we have not yet. We're still trying to ingest all of our data to see if patterns change. I don't think they will much, but we haven't really done any sort of offset correction to try to improve ourselves to a one-to-one. Some of those relationships probably aren't tight enough to justify that, to be honest.
Okay, folks, we are at time. If anybody has other questions that they want answered, you can feel free to throw them into the exit survey on the way out. It'll close as you leave the webinar session. If you have a few minutes, please do take the webinar survey, because it does help us kind of develop how we do the webinar series, and I do actually read the comments. So if you have nice or otherwise things to say, that's a good place to put them. Next steps, the webinar recording will be available in the next couple days. Usually only takes us 1 or 2 days to put it all together, so you can check the YouTube channel or the website for the recording. There's more webinars coming up. Next one is in 2 weeks. It's on April 1st. That's not a prank, it's a real webinar, so feel free to join us for that one. And with that, we'll just thank our presenters for taking the time to be with us today and for putting together such a great presentation and for answering questions. Thank you to everybody who joined and who participated, and we'll see you in the next one. Have a great day.